wonderful background that history of chemistry made for the teaching of chemistry through Peter, and later on through many other acquaintances that I learned about actually through Peter. So I'm very grateful to be here today to speak about this interesting trio, Scandium, Gallium, and Germanium, 3 elements discovered by looking at Mendeleev's speculative periodic table. So first of all, I'd like to mention that this particular paper came about because of a symposium that was organized and also carried out at the American Chemical Society National Meeting in San Diego in 2019 in celebration of the International Year of the Periodic Table. And then it was subsequently rendered into a volume called 150 Years of the Periodic Table, a commemorative symposium, edited by Carmen Junta Virmines and Gregory Girolami. And a chapter in this particular volume, chapter 10, is the chapter that developed from the symposium, the talk that I gave in the symposium, and from that actually arose the talk that you'll be hearing this afternoon. So it was published by Springer in 2021, and you may want to take a look at it. I would go to a lending library to borrow it because you'd probably end up spending a little more than 80 or 90 pounds on it if you wanted to buy it. It's 150 US dollars. At any rate, we'll get on now with taking a look at these 3 interesting elements. And as you can see in the cover here, that they are highlighted in pink, Scandium, Gallium, and Germanium in that order in the periodic table. What you also will notice, however, is that there are other elements in this table that are highlighted in gray. And I will get to those later because they figure somewhat in the discussion about discovery, like who discovered what, when, where, how. And it's not a simple matter to talk about elemental discovery anymore, such as somebody digging in the earth, finding something and saying, Eureka, this is a new element, etc. So it gets much more complicated as time goes on. So let's take a look then at these first 3, what you'd call iconic elements that were noticed by Mendeleev when he organized the elements that he had to hand in a table according to the organizing principle of atomic weight. And if you take a look at this table, you see that there are 3 red circled areas with question marks. And these question marks are the ones that I'll be talking about initially in this talk. And they happen to be, as you can see, atomic masses of 45, 68, and 70, according to his table. Now we have to keep in mind that his organizing principle was reasonable at the time. Of course, we now know that the principle is atomic number, not atomic weight. But actually, this was close enough at that time. And of course, it failed in many other instances, mainly because of a lack of knowledge of just how many elements there were in a period, but not only that, the erroneous atomic weights that were to hand at the time. So if we take a look, then we'll take a look at these 3 elements and we'll do their chronology and we'll look at their how they were discovered and who did it. And the first one is gallium, and it was discovered by Lecoq de Beaubardron, who was a member of the Protestant French nobility, but reduced to poverty because of the revocation of the Edict of Nantes, that is, the Edict of Toleration of Protestants in France. And so he couldn't afford to go to university. He had to work on his family farm, in a sense, which basically was a winery. But he got so interested in elements, especially the rare earth elements, because of their colors, when he saw them at the École Polytechnique in Paris. And so he didn't go to university, but he studied the syllabi at the university, and on his own developed spectroscopic techniques and theory, so that now he is considered one of the founders, along with Bunsen, Virchow, and Crookes, of spectroscopy. So what he suspected in 1863, note that this is before Mendeleev's publication in 1869, he suspected an element between aluminum and indium, and he then did a spark spectrum in 1875 where he actually saw unknown lines at 417 and 404. Now these we call nanometers now, but he had to isolate the substance from 52 kilograms of zinc blend. So imagine carting in 52 kilograms of anything, and I think you can see that he was dealing with an awful lot of work here. So he must have been on the track of something. And in November of that same year, he isolated 1 gram of this material that he now realized was a new element, but now from a much larger amount of the ore, 300 kilograms. And then later on, he was able to isolate, and a few years later, 75 grams of this element from 4,000 kilograms. Now, remember, he was a poor erstwhile student. Where was he getting all of this from? Friends. But at any rate, what he called this new element was gallium. Some people thought that he was naming it after himself in a sense, but he actually was naming it after the country of France, Gallia in Latin. And he actually was able to show by later on measuring properties that the properties that were predicted by Mendeleev were quite accurate. Mendeleev predicted an atomic weight of 68, turned out to be about closer to 70. He predicted a very low melting point. The melting point is actually below the temperature of a human body, so you can actually melt this stuff right in your hand. The density was very close, and also the formulation of compounds, how they would form with oxides and chlorides and so forth. So actually, what we have to realize that the Beauvardron was not just a flash in the pan. He was quite a star because he also later discovered samarium in 1880, discovered dysprosium in 1886, was the first to isolate gadolinium in 1886 as well, and he identified europium spectroscopically in 1892. And then when Sir William Ramsay discovered argon, it was actually Lecoq de Beauvardron that suggested that there might be a whole family of these elements, hitherto unsuspected. So he was quite a star. And I want to say a few words here about gallium. There's an average crustal abundance of about 18.7 parts per million. It's number 34 in crustal abundance. It's very large liquid range, and so it's used in large range thermometers, and it has a number of applications. And of course, it's made famous by Sam Keene's book, The Disappearing Spoon, because you just dunk a spoon of gallium in hot water, and of course, it will melt. And of course, Oliver Sacks made it famous too, because it was his favorite element. So if we move on now to the second star in our show, that is Scandium. It was discovered by Nielsen, and Nielsen actually came from a very rural background and went to Uppsala, probably the first in his family to study, especially in the sciences. But he interrupted his studies because of ill health, took a year off, eventually recovered his health, and eventually received his doctorate and became the head of the laboratory that Jan Berzelius had vacated in 1848. His initial research was on the chemistry of beryllium and selenium, and what he realized later on in looking at the literature is that Per Theodor Cleve found that the spectroscopic bands of erbium were split into two groups, yielding thulium, and Marignac discovered terbium, but he said, look at these rare earth supplies more closely if you have large supplies of them, because there's an awful lot left in these rare earths. And as a matter of fact, the rare earths began to yield new elements like Russian dolls, just coming out one after one. And Nielsen started studying the minerals of the rare earths, and he had a greater quantity of these minerals than any other chemists. And then he began to look methodically at what the elements were Mendeleev called eka were, namely the first beyond the element that is in the same grouping that Mendeleev had proposed. And what he found that in fractionating nitrates of the euxenite and gadolinite, that he separated among the insoluble basic salts a nitrate of lower atomic weight. He really didn't expect that. And as a matter of fact, it turned out to be what we now call eka boron. But he didn't realize what he had actually discovered then. He just knew it was something new. It turned out to be very close to what Mendeleev had predicted for the so-called eka boron, but it was actually Theodor Cleve who pointed out the identity of scandium as Mendeleev's eka boron. So Nielsen prepared the oxide of scandium. He never prepared the pure element, but he did actually isolate the oxide, and so he's given credit for its discovery. But the element, actually the metal, was not isolated until 38 years later in 1937 in the Freiburg in Breisgau department by Fischer, Bringer, and Greneisen. What about scandium? It's 21.3 parts per million, number 35. It's kind of rare, so it's expensive, and it has a few applications, as you can see, in high performance alloys and metal halide lamps. So if we move on to our next star, germanium, it was discovered by Clemens Winkler. Winkler's father, Kurt, was a metallurgist who studied under Berzelius, so Winkler came by his chemistry honestly. He went to the Freiburg School of Mines, very famous and oldest school of mines in the world, in 1857, then went on to graduate work in Leipzig, returned as the professor of chemical technology to Freiburg in 1873. Now, in 1885, a turning point came when one of the professors there, Alvin Weisbach, discovered a new ore, and he named it argyrodite and asked Winkler, who was a very fine analytical chemist, to do a thorough quantitative analysis to determine its composition. But no matter how hard Winkler worked, he consistently came in at 7% too low in terms of the quantities of material in this particular ore. And he worked and toiled at the problem for months and months and months, having precipitated out, and all he ever found in his filtrate was what he thought was sodium chloride. So about to give up, he just threw a bunch of concentrated HCl into the filtrate, and lo and behold, what turned out to be insoluble be turned out, or turned out soluble, turned insoluble, because this new element was actually insoluble in concentrated acid, which he had just then created, but was soluble in dilute acids in water, which was what he was seeing initially in his filtrate. And so the question was, what is it? And where did this thing belong in the periodic table? It was quite a problem for people. They thought, first of all, that it was going to be between antimony and bismuth. That's what Winkler thought. Then later, when Winkler and Mendeleev and Lothar Meyer corresponded, Mendeleev suggested its placement under cadmium in his table. But it was actually Lothar Meyer who was the one who suggested that it was actually silicium. Silicium was a German name for silicon. And Winkler called it germanium. People objected to that because it was too nationalistic. Well, what about scandium being Scandinavia and gallium being France? It was okay, I think, for most people. And then, of course, they recognized that it was a nonmetal, and should it have an IUM ending? Well, I guess if silicium was okay for Germany, then germanium was okay for this new element. But it was actually Lothar Meyer who identified it and placed it in the periodic table. So in summary, again, we see that the properties predicted by Mendeleev were pretty accurate again. The atomic weight, 72, about a very high melting point, a density of about 4. 4.7 was the prediction, 4.23 the actual, and then of course the formulation and so forth. So silicon then became germanium. What about germanium? It's number 52. It has only a crustal abundance of 1.6 parts per million, so quite rare. It actually solidified the definition of what we now call metalloids, those hanging about in between the metals and the nonmetals. And it actually was a key to the advent of the information age because it was a key component of point contact transistors. And that was back in 1947. But however, it was also, of course, something else we'll see on the next slide. But I just wanted to point out that germanium was just the one atom among others in the original mineral argyrodite, which meant, of course, that it was not very abundant. And argyrodite itself was a very rare mineral. And so for germanium to become an important element for the information age pointed to some problems. Winkler was able to get 52 kilograms of this ore, and he actually succeeded in preparing a lot of compounds of germanium, chlorides, sulfides, dioxide, and actually even the first organogermanium compound, tetraethyl germane. And as I mentioned before, from 1947 and now up until 1956, germanium was extremely important in the transistor industry because it could be made very pure. But then methods to purify silicon actually came to the rescue because germanium was pretty rare. And as we know, silicon is quite abundant, one of the most abundant elements on Earth. And so being able to purify silicon actually led to a great increase in the transistor industry and caused us now to name the place Silicon Valley instead of Germanium Valley. And right now, germanium is used chiefly in fiber optics and as a catalyst in polymerization. So now we get to a question about these three. Who discovered what? If we take a look at the three elements that we might call elements of speculation, namely elements of discovery, namely speculation, detection, and isolation, or sometimes people call this whole row of things effective discovery, what we notice is that Bois Baudran, hands down, can claim absolutely discovery of gallium. It's he who kind of thought about it, speculated about its existence long before Mendeleev's table. He then identified it spectroscopically some years later, and then in that very same year, he was able to isolate the element itself. So he gets that credit. If we take a look at scandium, however, what we see is that Mendeleev was the one who, of course, speculated on it. Nilsson discovered in 1879, 10 years later, the oxide and the nitrate. But he never isolated the element. He only isolated compounds of the element. And furthermore, he didn't even know what he had until it was Lothar Meyer who pointed it out. And then it was only in 1937, so quite a few years after Nilsson's death, that it was isolated as an element. So who gets credit for the discovery? Nilsson is normally given credit, traditionally given credit, but we do have to look at this other work that took place. Now, there are some others that are a little bit more problematic, and we'll get to those, but let's take a look at germanium. Germanium was speculated on by Mendeleev, as we can see. It was detected and then isolated, hands down, by Winkler in the year 1886. So Winkler does indeed, and rightly so, gets credit for the discovery of germanium. Well, now let's go back here to the original periodic table that we saw on the cover of this slideshow. And I think you can see there are a lot of gray areas. And they are indeed gray areas. And we'll take a look at some of them here. And I'd like to begin by taking a look at the discovery of europium and gadolinium. And again, we have to ask ourselves, speculation, detection, isolation, or something else. So, europium, it was actually detected spectroscopically by Bois Baudran in 1892, but he didn't know what he had. He simply saw some unknown lines. It was Anatole de Marseille in 1896, so 4 years later. Maybe I think I know what this is. It's probably, there's a rare earth, and I think I know how to get around to isolating it. And he was a very, very fine chemist in that regard. And sure enough, 5 years later, he managed to isolate europium. So I guess the question is, who discovered it? Bois Baudran detected it, but he didn't know what he had. De Marseille isolated it and also speculated on it, so he gets the credit. Now, gadolinium is another instance of who gets the credit, because it was detected spectroscopically by Marignac, Galissard de Marignac, in 1880. It was isolated as the metal 6 years later by Bois Baudran. So I guess they have to share credit for that determination. But I think you can see, if you look through elemental discovery, and I guess John Emsley's book on that is the best reference, you see that things are not cut and dried. sometimes it's a little bit difficult to determine that. And so we've taken a look now at europium and gadolinium. Let's take a look at another very famous pair, rubidium and cesium. And I think you all know the story of rubidium and cesium because actually they ushered in the era of spectroscopy, because it was Robert Bunsen and Gustav Kirchhoff who developed a prototype spectrograph using Bunsen's burner as a light source. And it was they who, using that spectroscope, actually discovered in 1860, 1861, the lines, the red lines of rubidium and the bluish lines of cesium, which gave them their names, by distilling out 600 quintals, or about 44 tons of spring water or spa water, in order to detect those lines. But they only detected them. They never actually were able to isolate these two elements. And it was only in 1882, many years later, that a student, Carl Zetterberg, working in Bunsen's lab, who actually was able to isolate and was able to determine the properties of these two elements. So I think you can see there's a question here. We always give Bunsen and Kirchhoff the credit. People now are saying that Zetterberg also ought to have the credit. And you will find on the RSC website, as a matter of fact, a little essay about that written by Alan Bronsfield. So you might want to check that out. So now we'll take a look at another famous pair, and these are praseodymium and neodymium, right here, pair here. And I think the first thing we ought to say was that these two twins, if you will, were once thought to be a single element called didymium. And right now we know, of course, that they've been isolated into praseodymium and neodymium, actually named by Auer von Welsbach, Karl Auer von Welsbach. But in 1882, Bohuslav Brauner, working in Robert Bunsen's laboratory, speculated about this pair. He didn't know it was a pair. He speculated about didymium, and he speculated that they may contain more than one element. Wasn't sure, but he thought about it and said so. And the conventional story goes that Auer von Welsbach, working in that same lab, overheard this discussion, went home to Austria, to Vienna in 1885, and set about trying to isolate these elements, succeeded after many years of very, very intensive fractional crystallization work. He was able to detect the spectroscopic lines, and then he was able also to isolate the two elements, and still using the name dymium. Instead of calling it didymium, he has now praseodymium, because praseo being a prefix for greenish, because it gave green salts, and neodymium, new didymium in a sense. And originally they were called praseodidymium and neodymium. Now, this is interesting because Auer did all the heavy lifting, but it was Brauner who came and said that he had been plagiarized by Auer von Welsbach because it was he who had first discovered the elements. But Brauner merely speculated on them. So the question is, like, who gets the credit? Brauner tried to claim all the credit, but was more or less dismissed by the scientific community. So now we come to another interesting discovery, and that is the question of helium, which you see all the way up there in the upper right-hand corner of the periodic table. And another interesting thing about this particular discovery is that we have two names associated with helium, the discovery of helium. We have Janssen, a French astronomer, who actually first detected it at a solar eclipse in 1868. But it was also Norman Lockyer, British, in the same year, who realized that it was a new element, that it was discovered in the sun. And so, since Helios is the Greek for sun, he named the element helium. So he kind of ended up with naming rights, but Janssen and Lockyer both received credit for the discovery by detection. It was 1895, some years later, that Père Clèves and Langlais both were able to actually isolate it as emanation from radiation from uranium. So helium, again, was not isolated until some years after its detection, but Janssen and Lockyer received the credit. Now, thallium is another interesting element in that both Crookes and Lamy in the same year detected it, and they also in the same year were able to isolate it. And so the two of them received the credit for that. So let's move on now to the element promethium. Now, I think you can see Browner crops up again, this time in 1902. And Browner, I quote here, is something that he wrote. Apart from the 10 elements already listed and more or less accurately studied by me, about 7 to 10 additional elements could be placed in this group. It is not impossible that one would be able to split neodymium into at least one element with a smaller atomic weight and into another with a higher atomic weight, about 145, and similarly some more gaps lying between cerium and tantalum could be filled. All right, so lots of speculation here, lots of speculation. And of course, promethium was eventually discovered, but not where people thought it was going to be. Remember that it turns out that it's one of the elements that was giving people a thorn in the side because it was in the main group of the periodic table, but simply couldn't be isolated. It couldn't even be detected. And people thought they had done so, and there's a whole line of people who thought that they had discovered this element. And it wasn't until the byproducts of uranium fission at the Oak Ridge, Tennessee nuclear reactor were analyzed that this element was discovered, found to have only radioactive isotopes, no stable isotopes, and very relatively, according to the age of the Earth, short-lived isotopes, and therefore most likely would never be discovered if you started pawing around in the mineral content of the Earth, except in one place, and that is there's a natural nuclear reactor down in Gabon called the Oklo natural reactor, which could indeed be a source of finding promethium naturally, because this reactor is constantly renewing itself, except that right now it's being mined out, probably mined out already, but there's an interesting article about this in the Scientific American in 2011, I believe. So we come back to Browner. He arrived at the conviction that the gap between neodymium and samarium was abnormally large. He read a paper in St. Petersburg in 1902. The conclusion was not reached by any chemist before, that the following 7 elements possessing now, all right, so now, remember, he's talking atomic numbers. He read his paper in 1902, where the concept of atomic number did not yet exist. But now he's saying atomic numbers 43, 61, 72, 75, 85, 87, and 89 remain to be discovered. And as regards element number 61, the difference between atomic weights of samarium to neodymium is 6.1, and it's greater than that between any other 2 neighboring elements. When did he write this? He wrote it in 1926, so very long after all of people knew about much of this. But at the same time, he is now claiming more or less to be the discoverer of these other elements by speculation. I guess Mendeleev is actually having the last laugh over all of this, because he actually was the first to organize the principle, and he, I think, is the one who probably still ultimately deserves the credit for much of the speculative part of this talk, at any rate. Now, in 1976, Yuri Soloviev gave an analysis. First of all, he said there can be no doubt that the fundamental content of the principle of periodicity was quite clear to Mendeleev from February of 1869, and that it served as a guide to expand upon the system of the elements. Secondly, he said that Mendeleev emphasized that every natural law gains its particular scientific significance whenever it is possible to derive practical consequences from it, and that is, logical conclusions that explain what has not yet been explained and pointing to phenomena unknown from the beginning, and then above all, by carrying out controllable predictions by experiment. So he laid out the process for discovering new elements. Now, of course, we know that of particular significance, the prediction of the existence of Gallium, discovered by Beaubandron, boron by Scandium by Nielsen, and silicon germanium by Winkler were most important, such that the discoveries of these elements, first of all, gallium, actually began to change the attitude of the scientific world with respect to the periodic system of the elements, but not right away. It was decisive, but gradual. Apparently, according to Emily Dickinson, she said, "The truth must dazzle gradually, or every man be blind." So this truth dazzled gradually. And we have to keep in mind, though, that Mendeleev had big ideas. And he wasn't interested in simple priority disputes about elemental discoveries. He wanted what you'd call the whole Megillah. He wanted credit for the entire periodic system. And he said in a letter to de Canvel in 1879, "It's now evident that the periodic law leads to consequences that preceding systems did not dare to predict." He says, "At first, it was only a scheme, a grouping, but the periodic law renders the facts subsidiary to the principle." So he's talking now about a philosophical principle that governs the mysterious nature of the elements. So this is what Mendeleev rather ferociously throughout his life contended that he deserved the credit for. But we can't neglect Lothar Meyer, because in 1870, Meyer, although he was unaware of Mendeleev's study, had also been working on a periodic table of sorts with 56 elements, and he also maintained that the properties of the elements are periodic functions of their atomic mass. And in fact, his very famous plot of atomic weights versus atomic volumes shows this very, very clearly. And so what we really realize is that Meyer arrived at the fundamental concept independently of Mendeleev, and some of the papers by both Mendeleev and Meyer documenting their controversy you can find all in this particular volume of Verita. The Brits, you guys understood this by awarding the two of them the Curian lecture in the same year, jointly. And so I think that that was an indication that Meyer certainly claims priority to. So now we have to realize that the periodic table has now become iconic. It is actually illustrated here in a bunch of peeps, the marshmallowy things that you can buy around this season of the year, that it is recognized by students who put this periodic table together, that each of the elements is unique, and each of these little peeps has been decorated in some way with an indication of the uniqueness of each of the elements. And some of them, as you can see, are nationalistic in terms of who discovered them. That always it was Mendeleev who kept saying, Eka, 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 there's one more, there's one more, there's one more, Eka being one in Sanskrit. And of course, he also took his two other Sanskrit prefixes, dvi and dvi, and used them for 2 and 3 as well, because Mendeleev had once studied Sanskrit in St. Petersburg. And of course, there's Lothar Meyer, who came to his table a little bit late, was published a little bit late, and wished that he had published it sooner. And so I want to thank you very much for your attention. I think that we still have to allow our 3 stars to take a bow: Gallium, Scandium, Germanium. And then, of course, the person who has discovered, who now has his own element named after him, Mendeleevium, will also take a bow. And I do believe that it would be nice to have an element named Meyerium as well, although that has not come about, probably never will. And the other thing that's very interesting when I was doing this study is I found that Mendeleev had an awful lot of stamps developed honoring him in many, many countries, but I could not find a single stamp that honored Lothar Meyer in any country whatsoever. So if any of you have been able to discover that, I would be very interested in knowing about it, because Meyer has really, really receded into the shadows, even though at some point they seem to have been neck and neck in terms of priority for the principle of periodicity. So again, thank you very much, and I'd like to entertain any questions that may be found in chat at this point, if you'd like to share them with me.
Thank you very much, Mary Virginia Orna. Would you like to show us your book? Do you want to show people your book?
Aha. There's a question here. Crook speculated that a chemical element existed because of an unidentified green spectral line, which became thallium. Of course, Crook's LEMI led to a spectacular international priority dispute in the early 1860s. Yes, yes. Okay, show the book. I don't know if you'd be able to see it. Here it is. It's a beautiful bright pink, and what it says is 150 years of the periodic table, a commemorative symposium. And the lead editor on this is Carmen Junta, Giunta. He is also the editor of the Bulletin for the History of Chemistry. So if you want to take a look at the book, it's got a lot of good stuff in here. Chapter 10 by myself highlights these three elements and a little bit about the question of discovery. But the following chapter by one of your own countrymen, Simon Cotton, is on the rare earth elements themselves. He confines his discussion to the rare earth elements. I think you know that he's an honorary lecturer up at the University of Birmingham, and I think once was professor at Felixstowe College. So Simon and I correspond pretty regularly with one another, and I don't know if he's on this particular in this particular group right now or not. Anyway, I highly recommend these. And where is Henry Zeppa's question?
Can you see it in chat?
This is Frank James. Oh, hi, Frank. Yes, of course. Now let's take a look and see if I can find. And Frank James also said, John Herschel wrote that he who proves discovers. So I suppose we need to agree what proof means in this context. And that's very true, Frank, especially now, of course, with all the discoveries coming from synthetic elements and maybe 50 people involved, and therefore a problem with respect to assigning priority. Now here I found, Henry, I found your question. How does Niels Bohr's prediction of properties for element number 72 compared to those of earlier chemists for ECA elements? The history of hafnium in this regard is not well known nowadays. I wonder why. I'm not so sure I know why either. The question about hafnium, I think, actually comes down to the fact that von Felsbach and Georges Urbain, thought that they had discovered it by mining the rare earth minerals, and they thought they had discovered it, and they placed it at the end of the rare earths. But the story, I think, goes that using quantum mechanics, Niels Bohr predicted that element number 72 should not be found among the rare earths, but should be placed in the main group of the periodic table. And as a matter of fact, that actually sent Dirk, I'm trying to remember their names now, von Hevesy, right, and Koster. Von Hevesy and Koster went hunting for hafnium among the zirconium minerals. And if you notice here in the periodic table, if you can still see the screen here, that hafnium is directly under zirconium. And as a matter of fact, they discovered gram amounts of this new element, now known as element 72, hafnium, in the zirconium minerals. I think that is more or less the story on that. Henry, does that kind of address your question?
I think so. Well, we're going muted. So
all right, the Julius Thompson jumped
anyway,
in.
Mary Virginia, I think
okay.
you better be off to your
See, I'm not familiar with that. Thompson was a very, very famous chemist, but I'm not sure of his dates or whether or not he actually had speculated on that too. That would be an interesting thing to check out.
Oh yeah, thank you very much, Mary Virginia. I know you've got to be off to a funeral, haven't you, in a few minutes?
Right.
You've got a funeral to go to.
Yes. I have another unexpected engagement over which no one has control. I am on my way to a funeral that begins in a half an hour.
I think we better say goodbye to you, Mary Virginia. Thank you very much again for a lovely talk. That was a really fascinating talk.
Such a pleasure. I have really, really enjoyed speaking today with you all, and I certainly hope that I actually, when I can, I'm fairly regular participant in these lectures, and I think they are stupendous. They are absolutely fantastic, and I am so honored to have been invited to be among you. So thank you so much for coming, everyone, and may you all have a very, very happy spring, happy Easter, happy Passover, happy Ramadan, and any other holiday that people like to celebrate at this wonderful time of year. So thank you, and thank you, Henry and Frank and all my friends. Frank James, too, I should mention, was another person who was also very, very instrumental in my interest in the history of chemistry, because he, too, invited my students to the Royal Institution over many years. And not only that, beginning in the 1990s and right up until the beginning of COVID, at the end of 2019, I had a group of 20 Israeli students hosted by Frank at the Royal Institution. So thank you again. My roots are with you all, and I am grateful for them. Thank you.
Thank you. Thank you, Mary. Now, can I just say to everybody...
By the way, if any of you want to contact me, my email address is simply my name, Mary Virginia Orna @gmail.com. No spaces, of course. So anyway, I wish you all a very, very happy spring. Thank you so much. And thank you, Peter, again, for running such a marvelous forum. And I look forward to the next talk.
Okay, thank you very much, Mary.
Will we meet again? Thank you.
Thank you very much, everybody, for attending today. We had 72 people today, so that's one of our biggest audiences so far. Next week, I'll be talking next Tuesday, same time, same place. I'll be talking about the history of the chemical industry in the 20th century in our ongoing series about the history of chemistry. Of course, this is about the history of chemistry as well, but the other series is more programmatic, shall we say. And then next month, we'll have Peter Ramberg talking about the 19th century. And before that, Anna Simmons will be giving a talk about the Society of Apothecaries and the whole question of drugs and so forth. So next month, there'll be 2 excellent lectures. Next week, there'll be 1. Well, I don't know if it's going to be excellent, but it's going to be by me. Okay, bye, everybody. Have a good week. And we look forward to seeing you again in the not too distant future. Bye for now.